Hi everyone, this is Anand and today we will be discussing the problems and solution of CodeDrift. Hi everyone, so today in this video I will be discussing the problem least median. Okay, so the problem says that you are given an array A of length n. Okay, we are given an array of length n, right? And we have to find the number of odd length subarrays whose median is at least b. Okay, and what is a median? A median is defined as the middle element after the array is sorted. More formally, if the length of the array is m, then after sorting the array, its median is element at the m by 2th index, where this m by 2 is basically 0 indexed. Okay, for example, if we give you an array like 2, 5 and 3, then what will be its median? So before finding the median, you sort it first. So after sorting, it will look like 2, 3, 5. Okay, now you find the m by 2th. So what is m? M is here the length of the array. So the length of array is 3. So 3 by 2 is 1. So what is the element at the 1th index? So it is 3. So that's why the median of this array will be 3. Okay, so now let us look at some examples to understand it more clearly. So let's say we are given an array A like this, 1, 2, 3, 4, and we have to find the number of odd length subarrays whose median is at least b. Okay, and b is here given as 3. Okay, so we first enumerate all the odd length subarrays. Okay, so what can be all the odd length subarrays be? So you can have like 1, then 2, then 3, then 4, then 1, 2, 3, this one, and you can also have 2, 3, 4 like this one. Okay, so these are all odd length subarrays of this array A. Now you see how many of them are having a median which is greater than or equal to 3. So you will see that there are 3 such subarrays like this one, and this one. Okay, so here the median is 3, here the median is 4, and here the median is 3. Okay, now if you see this is not having a median greater than equal to 3, it is having median equal to 2, so we don't consider it. So here we are having 3 subarrays with median greater than or equal to 3, so our answer for this case will be equal to 3. Okay, so that's why our answer for this case will be 3. Similarly, if you consider the same array A and if you take the value of b to be equal to 4, then how many subarrays will be there? Okay, so there will be only one subarray with median which will be greater than or equal to 4. Okay, like you consider these subarrays, then only this array, okay, only this subarray has a median equal to 4 which is greater than or equal to b of this case. So that's why the answer in this case will be equal to 1, right? Now let us look at the approach. So how we can solve it. Okay, so before heading towards the approach, let us think of this question. Okay, that given an array A of n elements, how do we know if its median will be at least x? Okay, so let's say that if n is equal to 3 and x is equal to 2, how will the array A look like after sorting? Okay, so let's say you are having this one, right? So since n is equal to 3, then there must be place for storing 3 elements. Okay, now you are saying that how do we know that if its median will be at least x? Okay, now if you are having 3 elements, which element will be the median after sorting? So basically the element which will be lying at this position will be our median. Okay, and we want that it should be at least x. Okay, and x over here is 2, so we want that this should be greater than or equal to 2, right? And you are also saying that this is sorted. So this is the situation after sorting the array. So this is also sorted. So we know that any element which lies to the right of it will be greater than or equal to this element. Okay, but this element is itself greater than or equal to 2. So any element which will lie to the right of it will be greater than or equal to 2. Okay, we don't really care about this element, like all the elements lying to the left of it, they may or may not be greater than or equal to 2, but at least all these elements should be greater than or equal to 2, right? Okay, so similarly for n is equal to 5 and x is equal to 2, what you can notice is that the median of this array will be the element at this position. Okay, and since we want that the median should be greater than or equal to 2, the value at this position should be greater than or equal to 2. Similarly, the value at this position should also be greater than equal to 2. This should also be greater than or equal to 2. Okay, and we don't really care about what the value at these indexes will be. Now, since we are interested in finding the subarrays of odd lengths, that's why we are only investigating a sub arrays of sizes odd, right? So if you just generalize it for any n, and so if you just generalize it for any n and any x, what you can see is what you can conclude. Okay, so the conclusion over here is that for array of n elements, okay, and some x, okay, which is like, or some value of b you can see, because in the problem we are given b, so some b, so the array will look like in this way, okay, and this way, and let's say this is the middle element, this is, let's say, the middle element, and n is odd, let's say. So what we can say is that this the value of the element at this position should be greater than equal to b, this should also be greater than b, and all of them should be greater than or equal to b. Okay, and this is the thing. Okay, so what we can say is that the number of elements in the array which are greater than or equal to b should be greater than greater than the number of elements which are strictly lesser than b. Okay, because you see in the example which I gave you earlier, if you notice that in this case there were two elements, okay, there were two elements which were having its value greater than or equal to 2. So there are two elements, and the number of elements which can be strictly lesser than 2 can be at max 1. Okay, so even in that case this 2 will be greater than 1. Okay, similarly for this case also you can see that there are like 3 elements which are having its value greater than or equal to 2. Okay, on the other hand, there can be at max 2 elements which will be having its value strictly lesser than 2. Okay, so 3 is still greater than 2. Okay, so what we can generalize is that for an array of n, okay, sorry, what we can generalize is that for an array of n elements, okay, if we want the median to be at least b, okay, if you want the array to have its median to be at least b, the number of elements with value greater than or equal to b should be strictly greater than the number of elements with value strictly lesser than b. Okay, so this is the condition which is required. Okay, so now we have got this condition. Okay, we can also like simplify this as like this, like the number of elements so with value greater than or equal to b. Okay, we can just subtract it with number of elements with value strictly lesser than b, and this should be greater than 0. Okay, so this is the condition. Okay, so what it means is that the count of, okay, basically the count of elements with value greater than or equal to b minus the count of elements with value strictly lesser than b should be greater than 0. So how we can find this thing? Okay, so given an array, okay, so given an array with, let's say, any value like a1, a2, so on and so up to an. Okay, what we can do, if we just keep a variable which will store this difference, what we can do, we can just start iterating from the left, and for any element, if its value is greater than or equal to b, we will simply increment our difference. Okay, and if the value is lesser than b, strictly lesser than b, then we will decrement our b. We will decrement our difference. we will decrement our difference, and if it is greater than or equal to b, we will increment our difference. Okay, so if we just calculate this difference over this entire array a, and if this difference comes out to be greater than 0, strictly greater than 0, then we can surely say that this array a will be having its median, which will be at least b. Okay, one another thing that we can also do is that for every element of array a, what we can do is that if that element is at least b, or you can say if it is greater than or equal to b, we can just replace it with 1, and if it is lesser than b, strictly lesser than b, then we replace it with a -1. Okay, so if you just replace your array a with this kind of thing, with then you will get an array of 1 and -1. Okay, and if you just sum them up together, so that will give you this difference only. So by just calculating the sum of this modified array a and checking if it is greater than 0, you can just easily find whether its median will be at least b or not. Okay, so for example, if you just take your array like this, 2, 5 and 3, and let's say you want b to be equal to at least 3. Okay, so now what we can do, like we check, okay, is 2 at least 3, or like is 2 greater than or equal to 3? No, so we replace with it -1. 5 is greater than 3, we replace 5 with 1. 3 is equal to 3, so we also replace it with 1. Now we find the sum of this array, it comes out to be -1 plus 1 plus 1 plus 1, it comes out to be 1, since it is greater than 0. So yes, we can say that this array will be having its median at least 3, which you can see also, like its median will be, if you sort it, you get 2, 3, 5, and its median is 3. Okay, so now we have reduced our problem of finding whether a given array will be having its median at least b or not, to a problem where we just need to find the sum of that array and just check whether it is greater than 0 or not. So what we can do, like whatever the initial array which we will be given, okay, we just convert it to another array, okay, which will be a sequence of 1 and -1, any arbitrary sequence of 1 and -1 depending on the value of the ai. Like if ai is greater than or equal to b, then we replace it with 1, otherwise we replace it with -1. Okay, now all we need to do is to just calculate the number of odd length subarrays such that their sum is greater than 0. Okay, because we know that the median will be at least b if and only if the sum of all the elements in that range is greater than 0. So the required answer, or you can say the required number of subarrays is nothing but equal to the number of subarrays of odd length. Okay, remember odd length, such that their sum is strictly greater than 0. Okay, so now we reduced our problem to finding the number of subarrays with odd length and with sum greater than 0. Okay, so what we can do now is that given the array a, okay, like a1, a2, so on and so up to a of n, what we can do, we can just check for every subarray. Okay, and yeah, like this will not be this will be some sequence of 1 and -1. Okay, like 1 1, since we modified it, right? So now what we can do, we can just check for every subarray from L to R, we find their sum and check if it is greater than 0 or not. If it is greater than 0, then we can simply increment our count of the required subarrays and simply return it. Okay, but if you see the time complexity of it, like there can be around order of n square subarrays, and checking whether their sum is greater than 0 or not will again require an order of n time complexity, because we will just iterate through that subarray and check if its sum is greater than 0 or not. So the overall time complexity in that case will be order of n cubic, right? Now one thing you may think is that why not we can just store the prefix sums. Okay, because you know that if you want to calculate the sum, okay, from sum from a range L to R, then you can also write it like the prefix sum. prefix sum till r minus prefix sum till l minus 1. Okay, so by using this technique you may just optimize it a bit, because now for computing the sum of a given sub array you need only order of 1 time. Okay, so from order of n cube time complexity, by using prefix sums you can optimize it to order of n squared time complexity. Okay, but let us try to think if we can optimize it further or not. Okay, so for optimizing it further we will simply extend the idea of prefix sum that we discussed now. Okay, so what we can say is, now we know that the sum of some range L to R is nothing but equal to prefix sum till R minus prefix sum till L minus 1, right? Okay, so I am writing P, and basically P will store the prefix sum. So now what we want that this sum of the range from L to R should be greater than 0. Okay, now you can also write it like this, that P of R minus P of L minus 1 should be greater than 0. So from here what you get, P of R should be greater than P of L minus 1. Okay, so we got something like this. Okay, we got something like this. So what does this tell? This tells that given an array P, okay, so we are now focusing on the array P, we have to count how many pairs of indices R and L minus 1 exist such that P of R is greater than P of L minus 1. Okay, so how we can do this? So for discussing the solution, there is a prerequisite that you should be knowing segment tree. Okay, because the solution that we will be discussing is segment tree. The optimal solution uses segment tree. Okay, so basically a segment tree is used for doing range updates and range queries, and it can do both the things in order of log n operations. Okay, log n time complexity basically. So now we know that what we have to do, we have to count the number of such pairs. Okay, so let's say that this L minus 1 is some L dash. Okay, so now let's say that, so what we got, P of R is greater than P of L dash. Okay, so we have to calculate the number of pairs R and L dash, okay, such that R is greater than L dash. Okay, and this condition hold that P of R is greater than P of L dash, and this thing like R minus L dash. Okay, so this will give you the length of that sub array. This should be odd. Okay, what it means is that R minus L dash modulo 2, or not like this. Yeah, you can say like, yeah, that R minus L dash modulo 2 should be equal to 1. Okay, so what it means is that R and L dash can never be even and odd simultaneously, so their parity can never match. So if like R is even, then L dash must be odd, and if R is odd, then L dash must be even, so their parities must differ. Okay, so these are the like the two restrictions that we must handle while dealing with the solution. Okay, so what we can do, we can just first of all we can just calculate this prefix sum array, and after calculating this prefix sum array, what we will do, we will just declare two segment trees. Okay, the first segment tree will be odd segment tree, and the second segment tree will be even segment tree. Okay, so we will use something known as segment tree. Now we will have two segment trees. The first one will be odd and the second will be even. So what the odd segment tree will do, it will just store like for every odd index like 1, then 3, then 5. Okay, for every odd indexed position, whatever is the value at that position, let's say this is P of I. Okay, so what this will do is that it will simply store the count of that okay, so we will be maintaining these two segment trees, odd and even. For odd segment tree will help us to calculate the count of values in odd indexes, and even segment tree will help us to query or get the range count for the elements which are present at even indexes only. Okay, so now if you just see this, it will look like, if you just modify this equation, this looks like that P of L dash should be strictly lesser than P of R. Okay, and L dash and R should be of opposite varying parity, so they should have a different parity. Okay, so these are the two conditions we need to take care about, and we need to count the number of such pairs of L dash and R. So let's say we are standing at some R. Okay, we are standing at some R. So let's say its parity is 0, which means the index R is even. Okay, so what we need to do, we need to count how many indexes are there which are of opposite parity to 0, which means which are of parity 1. Okay, which means we need to count how many odd indexes are there such that the value at that point, okay, which means that the value of P of L dash such that the value at that point is strictly lesser than the value at this index R. So the value at this index R is P of R. Okay, so this is P of R, and we need to count how many odd indexes are there to the left of R such that the value at those indexes are strictly lesser than P of R. Okay, so we can just easily get this count by just querying, or by just counting the number of indexes such that the value at those indexes are basically lesser than P of R. Okay, so the value should be lying between 0 to P of R minus 1. Okay, and we count it in the opposite parity segment tree. So this is like 0, so we will count it for 1, which means odd segment tree. Okay, so we will use this method. So what this will do, this will just return the number of indexes such that they are such that those indexes are odd, and hence odd segment tree is taking care of them, and also the value at those indexes lie between 0 to P of R minus 1. Obviously, if the values lie at within this range, then we are sure that that will be lesser than P of R. Okay, that will be lesser than P of R. Now, important thing, similarly we can do this for even indexes as well, like if for odd indexes as well, like if R instead of being even, if R is odd, then we check for the opposite parity segment tree. Like in that case we will check in the even segment tree that how many indexes are there such that the value at those indexes lie within this range. Now, important thing to notice is that the value of P of R can be will lie in the range minus n to n. Okay, so the value of any prefix of I will lie within the range minus n to n. Why? Because the prefix array is calculated on the modified array A, and modified array A is a sequence of 1 and minus 1, right? So in the worst case, what can happen is that we get all the minus ones. So in that case, the prefix sum of the entire array, like at this position, the prefix sum will be minus n. Similarly, if all the array A contains all the ones, then the maximum value prefix sum will be n. So that's why the prefix sum lie between minus n to n. Okay. Now for implementing the segment tree, we will just keep two arrays. Okay, the first one you can say odd, the second one you can say even. Okay, now both these odd and even odd and even arrays will be doing what? Like if you consider, let's say, even array. So what even array will represent? So the even array will represent that if you consider any index of this even array, let's call it I. So even of I will basically store count of indexes such that the value at those indexes in the array P is I. Okay, so Similarly, odd will do the same thing, but that will just keep count of odd indexes, whereas this even will keep count of even indexes only. So even of I will store like how many even indexes are there, okay, how many even indexes are there in the original array, such that the value at those even indexes is equal to I. Okay, so this thing this thing will be stored in even, and similarly for odd also we will have something like that. So what can be the, since the even of I is like the value at those index is I, so since p of I lies between minus n to n, what we can do, we can just add plus n to all the elements of the array p. So adding the value n to every element of p will make p of I lying between 0 to 2n. Okay, so now our pi lies within this range. Okay, so now once our pi lies within this range, this thing holds now. Okay, because earlier we cannot have like even of I, so I cannot be negative. I can be 0 and positive, but it cannot be negative. That's why we just normalized p of I, like we added to every element p of I a value n, and now the pi is lying within range 0 to 2 times n. Okay, now we start processing the array p from left to right, and let's say if we are at some index I, we check what is its parity. Like if the index I is odd, what we do, we just simply check what is the value of p of I at that index. So let's say this is p of I. So if the value at this point is p of I, what we do, and we know that I is, let's say, even based even, then we for this even array, what we do, we just go to the position p of I. Let's say this is the index p of I, and initially it was all filled with 0. Now we just increment it by 1. Okay, and similarly we just keep on doing this for every I, starting from left to right. Okay, and whenever we need the sum, like whenever we need this thing, that how many like this count, like how many indexes are there within this range 0 to p of r minus 1 in a particular segment tree, we can easily count that using standard segment tree functions like update, get. Okay, so those things you can easily implement and uh, get the count and update the things all in order of log of n. Okay, so so now let us look at an example. So let's say array a is like 2 5 3 and b is 3. Then we convert this array to a to or array of 1 and minus 1, so it become like this. Okay, after that you calculate the prefix array of this array, so that will be 0 minus 1 0 1. We added a 0 at the beginning in order to handle the case where the subarray can be some prefix. Okay, after that we added 3 to all of them, because as I said, in order to make all the elements of the prefix array to be non-negative, we just added plus 3 to everyone, so it will look like this. And these are the indexes like 0 1 2 3. So 0 is even, 1 is odd, like this. Now we made two array, odd and even. Initially all of them will be filled with 0. So now we will just iterate from 0 index in our prefix array. So we see that 0 is an even number, so we check for the odd one. Okay, we check for the odd one, that what is the sum of the elements in the indexes from 0 till 3 minus 1, which is 2, in the odd array. Okay, so in the odd array the sum from 0 to 2 is 0. So in the answer, okay, so in the answer we didn't added anything. Okay, 0. Then we just move to the next index. Okay, but before moving to the next index, we updated the value in the even array. So what we will do, we will just simply say that at the position number 3 we will increment the value by 1. Okay, so it become 1. Now we move to position 1. So 1 is a odd, so we check for the even. So what is the sum of the value in the range from 0 to 2 minus 1, which is 1. So 0 to 1, which means this one. Okay, the range sum is 0, so we again added 0 only. Then we move to the next index, but before moving we just update the value. So since the index is odd, we update the value at position 2 to be get incremented by 1. So this will get incremented by 1. Then we move to the next position. This position is an even index, so we check for the its opposite, so odd index. So what is the range sum from 0 till 3 minus 1, which is 2. So the range from 0 to 2 is 1, so we add 1 to it, and after that we update at the even indexed array at position 3 to got incremented by 1. So it again got incremented by 1, it become 2. Now we move to position 4, position 3, which is odd, so we check for its opposite, which is even. So what is the sum, what is the sum in the range 0 to 4 minus 1, which is 3. So you see that the range sum 0 to 3 is 2, so we'll add 2 to it. So as a result we will get our answer as 3, and you can notice also that the answer will actually be 3, because when b is 3 you can mainly take these subarray, this subarray and this subarray. Okay, and yeah, these are the only 3 subarrays of odd lengths which will be having its median at least 3. Okay, so now let us look at the pseudo code for it. So we have defined a function find, and it will be accepting an array and of size n. So what we do, we just iterate for I is equal to 1 to n. If a of I is greater than or equal to b, we set ai to be equal to 1, else ai is equal to -1, right? Now we declare an array p of size n. Initially p of 0 is equal to 0, and then we go from 1 to n and do p of I is equal to p of I minus 1 plus a of I. So this is basically calculating the prefix sum array, right? Now once we have calculated this, we just add to every element of p of I, we add n, so that pi is non-negative, right? Now after that we declared two arrays of size 2 times n plus 1, and initially all of them will be containing zeros only. Now after that we declare a variable answer. So initially answer will be 0. Answer will be used for storing the count of the required number of subarrays. So answer is initially 0. Okay, after that what we do, we just iterate from 0 to n, right? We just first of all find what is the parity of this. Okay, parity 0 means even and parity 1 means odd. Okay, now whatever is the parity, what we do, we just count, we just use this count function, that how many indexes are there, okay, in the range 0 to p of I minus 1, such that it has a parity of 1 minus parity. So 1 minus parity basically represents the opposite parity. For example, if the parity is 0, then 1 minus 0 will be 1. Similarly, if the parity is 1, then 1 minus 1 will be 0. Okay, so in the opposite parity segment tree, we will count how many indexes are there, such that the value at those indexes lies in this range 0 to p of I minus 1, by using this count function. After counting the required number of subarrays, we also update the value at the position p of I to be incremented by 1. Okay, so this update will do what, that depending on the parity, like if the parity is odd or even, depending on that, we will just update the value at that index by increasing it by 1, right? And at the end we just simply return the answer. Okay, so the time complexity of this solution will be order of n log n. Why? Because we are just iterating for I is equal to 0 to n and counting and updating things. So counting and updating using segment tree usually takes order of log n time, and the space complexity of this will be also order of n, because we are using here two arrays like odd and even for storing the maintaining the segment tree, and moreover we are also using this prefix sum array, and moreover the language specific implementation will also need not language specific, but for implementing a segment tree you will also need to have another segment tree array, which is generally of the size of 4 times the size of nodes you will initially be having. Like if you want to build a segment tree on n indices, you will need a segment tree of size 4 times n. but still, like, adding all of them will actually give you a space complexity of order of n, or even like a small constant number of multiples of n, like maybe 8 times n or 4 times n, but we call it a simply space complexity of order of n. Okay, so I hope it's clear to you. Thanks. So if you enjoyed the video, please like, share and subscribe our channel. Thank you.